Hello everyone, my name is Chinta MVS Teja. Currently, I am pursuing BTech second year in Information Technology from Institute of Aeronautical Engineering. Today, I am going to give a presentation uh, of AAT concept video of the subject Computer Networks. So, the title of the presentation that I am going to explain is Switching Techniques. So, let's continue the presentation. The evolution of networking switching techniques. In the early days of computing networking, connecting devices was a chaotic, inefficient process. As organizations grew and the internet expanded, the limitations of simple point to point connections became painfully obvious. The breakthrough came with switching technology, a fundamental innovation that transformed network communication from broadcast chaos to intelligent targeted delivery. Today, switching forms the backbone of every modern network, from small office LANs to massive data centers powering the internet itself. Switching. Switching is the process of transferring data packets from one device to another in a network from one network to another using specific devices called switches. There are three types of switching methods: message switching, circuit switching, and packet switching. Firstly, circuit switching. Circuit switching is a communication method where a dedicated communication path or circuit is established between two devices before data transmission begins. The circuit remains dedicated to the communication for the duration of the session, and uh, no other devices can use it while the session is in progress. Circuit switching is commonly used in voice communication and some types of data communication. As you can see in the given image, how the communication path is going from one switch to another switch, from one device to another device using switches. Advantages of circuit switching. Guaranteed bandwidth. Circuit switching provides a dedicated path for communication, ensuring that bandwidth is guaranteed for the duration of the call. Low latency. Circuit switching provides low latency because the path is predetermined and there is no need to establish a connection for each packet. Predictable performance. Circuit switching provides predictable performance because the bandwidth is reserved and there is no competition for resources. Suitable for real-time communication. Circuit switching is suitable for real-time communication such as voice and video because it provides low latency and predictable performance. Packet switching. Packet switching is a communication method where data is divided into smaller units called packets and transmitted over the network. Each packet contains the source and destination addresses as well as other information needed for routing. The packets may take different paths to reach their destination, and they may be transmitted out of order or delayed due to network congestion. Advantages of packet switching. Efficient use of bandwidth. Packet switching is efficient because bandwidth is shared among multiple users and resources are allocated only when data needs to be transmitted. Flexible. Packet switching is flexible and can handle a wide range of data rates and packet switches. Scalable. Packet switching is highly scalable and can handle large amounts of traffic on a network. Lower cost. Packet switching is less expensive than circuit switching because resources are shared among multiple users. So now I'm going to talk about message switching. The entire message is sent as a single unit from one node to another. Each intermediate node stores the message and forwards it later. Store and forward technique. No dedicated path is required. Advantages. No need for a dedicated communication path. Efficient channel utilization. Disadvantages. Requires large storage at nodes. High delay in message delivery. Why switches matter? Why switches matter? Solving fundamental network challenges. Switching technology addresses three critical problems that plagued early network designs. Each of these solutions represent a significant advancement in network efficiency and performance. Forwarding the decision problem. When a packet arrives at a switch, the most immediate question is which output port should this packet be sent to? Forwarding determines the correct outgoing link based on the destination address. Without intelligent forwarding, every packet would have to be broadcast to all devices, creating massive inefficiency. Routing. Understanding network topology. While often handled by separate routing protocols at the network layer, Layer 3 switches contribute to routing by understanding how nodes are interconnected. Modern switches can be participate in routing decisions, maintaining routing tables that map network addresses to specific paths through the network. Network sharing. Resource allocation. Switches efficiently divide link capacity among multiple simultaneous connections, unlike old Ethernet hubs that shared bandwidth across all devices. Switches create dedicated paths between communicating devices, allowing full speed transmission without contention. The core mechanism. How switches learn. Switches operate at a data link layer 2 of the OSI model, which is responsible for node to node data transfer within the same network segment. This positioning is crucial because it allows switches to work with hardware level addressing rather than higher level network addressing. MAC addresses, the hardware identifier. Every network interface card (NIC) has a unique MAC address, media access control address, burned into its hardware at manufacture. These 48-bit addresses are globally unique identifiers, typically expressed as six pairs of hexadecimal digits like 00 colon 1A colon 2B colon 3C and so on. Switches use MAC addresses to identify which physical device is connected to which switch port. MAC address table, the memory. Switches maintain a MAC address table, also called as lookup table or LUT, that maps MAC addresses to specific switch ports. When a device sends its first packet through the switch records the source MAC addresses and the incoming port number in this table. Over time, the switch builds a comprehensive map of which devices are connected to which ports. Dynamic learning, adapting to change. The beauty of the MAC address table is it's built dynamically without manual configuration. When devices move are added or removed, switches automatically update their tables and trees are typically aged out of a period of inactivity, ensuring the table stays current even as network topology changes. The switching process, step by step. Understanding exactly how a switch process each packet reveals the elegance of this technology. Here's the complete journey. Step 1. Data frame arrival. A packet arrives at one of the switch input ports. The frame contains source MAC address, sender, and the destination MAC address, the intended receiver in its header along with the actual data payload. Step 2. MAC address extraction. The switch reads the destination MAC address from the packet header. This head address is the key to determining where the packet should be forwarded. The switch also notes the source MAC address for potential table updates. Table lookup. Third step. The switch consults its MAC address table, searching for an entry matching the destination MAC address. This lookup operation happens at wide speed, typically in microseconds, using specialized hardware called content addressable memory. Step 4. Forwarding decision. If the destination MAC address is found in the table, the switch forwards the packet only to the specific output port associated with that address. This targeted delivery is what makes switches so efficient. Traffic doesn't flood to devices that aren't involved in the conversation. Step 5. Flooding for unknown destinations. If the destination MAC address isn't in the table, the switch broadcasts the packet to all ports except the incoming port. This ensures the packet reaches its destination even when the switch doesn't yet know where it is. When the destination responds, the switch learns its location and updates the table for further packets. The advantage. Why switched networks win? Switched networks offer several compelling advantages over older hub-based or broadcast architectures. These advantages explain why switching became the universal standard for modern networking. Dedicated bandwidth. Each device gets its own dedicated link to the switch, allowing full speed transmission without contention. For example, on a 1 Gbps switch, each device can simultaneously transmit at 1 Gbps to the switch. Scalability. Large networks can be built by interconnecting switches in the hierarchical topologies. Reduce collisions. Targeted delivery means packets only go where they are needed, dramatically reducing the chance of data collisions. Improved performance. Faster data transfer and less congestion result from eliminating unnecessary broadcasts. Enhanced security. Since the traffic is only forwarded to intended destinations, it's harder for unauthorized devices to intercept data. While not a complete security solution, switch networks provide inherent protection against casual eavesdropping. Quality of service. Modern switches support QoS features that prioritize critical traffic, ensuring time sensitive data like voice or video gets delivered first. Intelligent data flow. From broadcast carriers to targeted delivery. The transformation from hub-based networks to switch-based switch networks represents one of the most significant advances in computer networking. In hub-based networks, every packet was broadcast to all devices, creating network congestion and security vulnerabilities. Switch networks, by contrast, deliver packets only to their intended destinations. Hub-based networks, old approach. Every packet broadcast to all devices. Shared bandwidth causes contention, high collision rates, slow performance, easy to intercept traffic, maximum 10 Mbps or 100 Mbps share, switch networks modern standard, packets forward only to destinations, dedicated bandwidth per connection, nearly zero collisions provide improved speed, natural traffic isolation enhances security, 100 Mbps, 1 Gbps or 10 Gbps per link. The foundation of modern networks, LAN backbone technology. Switching forms the fundamental infrastructure of local area networks in homes, offices, and campuses worldwide. Every wide Ethernet connection you use connects through one or more switches, even if you never see the physical hardware. Enterprise connectivity. The large organizations rely on complex switch network topologies to connect thousands of devices, hierarchical switches, string designs with core distribution and access layer switches enable scalable high performance enterprise networks. Internet infrastructure. The internet itself depends on switching at multiple levels. Foundation for innovation. Understanding switching is essential for to understanding modern networking concepts like VLAN, spanning tree, protocol, and link aggregation, and software-defined networking. Switching transformed networking from a broadcast medium into an intelligent targeted communication system. It's the invisible infrastructure that makes the modern digital life possible. Thank you.